So hello my dear students, today we are going to go for next theory question and then we will go for a few examples on how to find the eigenvectors. We have already seen how to find eigenvalues, right? So see the question, if T from V to V is a linear transformation where V is a vector space of dimension n and lambda 1 lambda 2 up to lambda k are distinct eigenvalues of T with x1 x2 up to xk as corresponding eigenvectors, then this x1 x2 xk are linearly independent in V. So this distinct eigenvalue word is important. So the result is saying that eigenvectors corresponding to distinct eigenvalues are always linearly independent. I mean, suppose you are having some matrix A and 1 2 3 are the eigenvalues of A, corresponding to 1, suppose x1 is eigenvector, corresponding to 2 x2 and corresponding to 3 x3 is eigenvector. Since this 1 2 3 are distinct eigenvalues, then we can say that the set x1 x2 and x3 will be linearly independent. So this is the magic of this theorem. So without any delay, let us go for the proof. So over here, first of all, I have written the given things. I have let V be a vector space of dimension n and T from V to V be a linear map, and let lambda 1 lambda 2 up to lambda k be distinct eigenvalues of T with x1 x2 up to xk as corresponding eigenvectors, and we have to show that this x1 x2 up to xk are linearly independent. So we are going to use the mathematical induction in order to prove it. So my statement will be, if x1 x2 uh, uh, xk are eigenvectors corresponding to distinct eigenvalues lambda 1 lambda 2 up to lambda k, then these vectors x1 x2 up to xk are linearly independent. So this is my p of k statement. If for these vectors are the vectors corresponding to this word is important, the distinct eigenvalues lambda 1 lambda 2 up to lambda k, then we have to show that these vectors is linearly independent. So त्यांच्या आधीचं जे आहे आपण ते गृहीत धरणार आहोत आणि त्यांच्या नंतरचं आपण ते प्रूव्ह करणार. आता ह्या ठिकाणी 3 स्टेप्स असतील इंडक्शनमध्ये, तुम्हाला ऑलरेडी माहिती आहे. पहिल्यांदा के इज इक्वल टू 1 साठी, त्यानंतर इंडक्शन स्टेप असणार, आपण गृहीत धरणार की पी ऑफ एन इज ट्रू आणि त्यानंतर आपण प्रूव्ह करणार की पी ऑफ एन प्लस 1 इज ट्रू. आता पी ऑफ 1 स्टेटमेंट काय असेल, इफ x1 इज आयगन वेक्टर करस्पॉन्डिंग टू आयगन व्हॅल्यू लॅम्डा 1 किंवा करस्पॉन्डिंग टू आयगन व्हॅल्यू लॅम्डा असं आपण म्हणूया. आता डिस्टिंक्टला काही अर्थ नाही आहे, कारण की के इज इक्वल टू 1 साठी आयगन व्हॅल्यू फक्त एकच राहणार आहे. जर आयगन व्हॅल्यूज 2 असतील तर आपण डिस्टिंक्ट म्हणू शकतो ना. त्यामुळे पी ऑफ 1 स्टेटमेंट काय असेल, इफ एक्स इज अ आयगन वेक्टर करस्पॉन्डिंग टू आयगन व्हॅल्यू लॅम्डा देन एक्स इज लिनियरली इंडिपेंडंट. मग असं होईल का, जर एक्स ही आयगन वेक्टर असेल करस्पॉन्डिंग टू आयगन व्हॅल्यू लॅम्डा, हे आपल्याकडे आहे, मग आपल्याला असं म्हणता येईल का की एक्स लिनियरली इंडिपेंडंट आहे? म्हणता येईल का, कारण की आयगन वेक्टर जी आहे ती काय नॉन झिरो असते हे आपण आधी बघितलेलं आहे. आणि दिस single non and we know that the single non-zero vector is always linearly independent, therefore that eigenvector is going to be linearly independent, so no issues with it, therefore p of 1 will be true. Okay, that is what I have said. For k is equal to 1, we know that the single non-zero vector is always linearly independent and x1 is going to be non-zero as it is an eigenvector, therefore this x1 will be linearly independent and therefore p of 1 is true. Now the induction step. So induction step, we are going to assume that p of n is true. Meaning is, if x1 x2 up to xn are eigenvectors corresponding to distinct eigenvalues lambda 1 lambda 2 up to lambda n, then these eigenvectors are linearly independent. Now just try to understand the induction step. Whenever you are having n eigenvectors corresponding to n distinct eigenvalues, you can immediately apply the induction step and you can say that eigenvectors will be linearly independent. Okay, now we have to prove p of n plus 1 is true. So what will be my p of n plus 1 statement? If x1 x2 up to xn plus 1 are eigenvectors corresponding to distinct eigenvalues lambda 1 lambda 2 up to lambda n plus 1, then we have to show that these eigenvectors x1 x2 up to xn plus 1 are linearly independent. Now just try to recall the definition of eigenvector. Yeah, eigenvector, so x is said to be an eigenvector corresponding to eigenvalue lambda, or you can say lambda is said to be an eigenvalue if there exists x not equal to 0 belonging to r raised to n such that Ax is equal to lambda x, isn't it? Lambda is said to be an eigenvalue of a matrix A if there exists x not equal to 0 belonging to r raised to n such that Ax is equal to lambda x. Now since this x1 x2 up to xn plus 1 are eigenvector corresponding to distinct eigenvalues lambda 1 lambda 2 up to lambda n plus 1, what we can say? We can say Ax1 should be equal to what? Lambda 1 x1. Ax2 should be equal to what? Lambda 2 x2, and this will be continued, and we can say that Axn will be equal to lambda n xn, and Axn plus 1 will be equal to what? Lambda n plus 1 xn, right? So that is what I have written here. So our claim is to show now this x1 x2 up to xn plus 1 are linearly independent. So I am going to follow the usual method. So what I will say, let alpha 1 x1 plus alpha 2 x2 plus so on plus alpha n xn plus alpha n plus 1 xn plus 1 is equal to 0. And what I have to show? I have to show that this alpha 1, alpha 2, alpha n up to alpha n plus 1 are 0. Now I am going to apply t on both sides. So if I apply t on both sides, what I will get? T of alpha 1 x1 plus so on continued alpha n plus 1 xn plus 1 will be equal to t of 0, which is 0. Now since t is a linear transformation, this is same as alpha 1 t of x1 plus so on plus alpha n plus 1 t of xn plus 1 will be equal to what? 0. Whatever this equation is there, I am going to call it as some star, I guess. Let me see what I have called it over here. Yeah, 2. Okay, so this is my 2 equation. Remember, I am talking about this. Okay, so what is t of x1? But we already have the value of t of x1 as lambda 1 x1. Therefore alpha 1 lambda 1 x1 plus so on plus alpha n plus 1. याच्या आधीची टर्म काय असेल? Alpha n, and t of xn is lambda n xn plus alpha n plus 1, and t of xn plus 1 is what? Lambda n plus 1 xn plus 1 will be equal to what? 0, right? That is what we will get. Now observe this 2 carefully and 3 carefully. So this is my 3. Which one? This. So observe this 2 and 3 carefully. What you can see. So I have to use the induction hypothesis. When I can use induction hypothesis? If I am having eigenvectors corresponding to distinct values. But how many eigenvectors I want? I want n eigenvectors corresponding to n distinct eigenvalues, right? And then that eigenvectors will be linearly independent, we can say, with the help of induction hypothesis. So see what trick I am going to use here. So I am going to multiply this 2 by lambda n plus 1. Okay, why I am going to multiply this 2 by lambda n plus 1? Because see, the last term of 3 is alpha n plus 1 lambda n plus 1 and xn plus 1. It is not like that you should multiply by lambda n plus 1 only. You can multiply by either lambda 1, lambda 2, or lambda n, or either you can multiply by lambda n plus 1. Anything will work, but we will multiply by lambda n plus 1 because it is easy to understand. Okay, so I will multiply this 2 by lambda n plus 1. So my last term will be what? Alpha n plus 1 lambda n plus 1 and xn plus 1, which is same as equation 3. Observe carefully. Okay, so after multiplying by lambda n plus 1, I will get alpha 1 x1 lambda n plus 1 plus so on plus alpha n xn lambda n plus 1, and plus the last term will be alpha n plus 1 lambda n plus 1 and xn plus 1 will be equal to 0. Now what I will do is, I will call it as some 4. So I am going to subtract this 3 and 4. So if I subtract it, what will happen? This last term, okay, this last term will get cancelled out, isn't it? And once this last term gets cancelled out, what we are going to get? This I will take bit down. As you can see over here, this is my 2. So I have applied t on both sides. Since t is a linear transformation, we got this. Then we have used t of x1 is equal to lambda 1 x1 and so on. Now we have multiplied 2 by lambda n plus 1, and this is what we got. I have called it as 4. Now I have subtracted this 3 and 4. Okay, this is my 3. So after subtracting 3 and 4, what I'm going to get? So we can see that this first term and this first term. So after subtraction, you can take, I guess, alpha 1 and x1 common, isn't it? So I'll take alpha 1 common from the left hand side. What will be left out inside the bracket? It will be lambda 1 minus lambda n plus 1, and outside it will be x1. This will be continued. The last term, this term is going to get cancelled out after the subtraction. So what will be left out? Alpha n lambda n minus lambda n plus 1, and outside it is going to be xn, and the right hand side is going to be 0. So can you observe it carefully? What are these x1, x2 up to xn? This x1, x2 up to xn are eigenvectors corresponding to what? Distinct eigenvalues lambda 1, lambda 2 up to lambda n. Since what we have assumed initially, we have already assumed that this x1, see here, x1, x2 up to xn plus 1 are eigenvectors corresponding to distinct eigenvalues lambda 1, lambda 2 up to lambda n plus 1. So you can just focus on this, that this x1, x2 up to xn are eigenvectors corresponding to what? This distinct eigenvalues lambda 1, lambda 2 up to lambda n plus 1. So what can you say by induction hypothesis? You can say that this x1, x2 up to xn should be linearly independent. Now since they are linearly independent, what should happen to these coefficients? See, this is the coefficient of x1 and so on. This is the coefficient of what? Xn, and these are real numbers. Note, okay, lambda 1 eigenvalues are real and these alphas are already real numbers. So therefore these coefficients should be equal to 0, since this x1, x2 up to xn are linearly independent. So this will imply alpha 1 lambda 1 minus lambda n plus 1 equal to so on, I have written it here, equal to alpha 2 lambda 2 minus lambda n plus 1 so on will be equal to what? 0. This is by induction hypothesis, but since these eigenvalues are distinct, okay, since lambda 1 is not equal to lambda n plus 1, so therefore this quantity is going to be non-zero, therefore alpha 1 will be 0. Similarly this quantity is also non-zero, therefore alpha 2 will be 0, and so on. So in this way alpha 1, alpha 2 and so on up to alpha n will be equal to 0. Remember, but what we wanted to prove, we have started with which equation? We have started with this equation, and we wanted to prove that alpha 1, alpha 2, alpha n, and as well as alpha n plus 1 should be 0. But till now what we have proved? Till now we have proved that only alpha 1, alpha 2 up to alpha n is 0. So how to show alpha n plus 1 is 0? It is easy. Simply put the value of alpha 1, alpha 2 and alpha n in these two equations. So what you are going to get? You will get alpha n plus 1, xn plus 1 will be equal to 0. Since this eigenvector is non-zero, this will imply alpha n plus 1 is equal to 0. So therefore we have proved this, all the scalars alpha 1, alpha 2 up to alpha n plus 1 are equal to 0, and therefore this x1, x2 up to xn plus 1 are linearly independent, and that is what we wanted to prove. Okay, so you can see, since this xn plus 1 is non-zero, therefore this alpha n plus 1 is equal to 0, and therefore this is linearly independent, and therefore by first principle of mathematical induction we got our result. Okay, so this is regarding this theorem. So very beautiful theorem. So in this theorem we have proved that the eigenvectors corresponding to distinct eigenvalues are always linearly independent.